Forget GPUs. We squeezed a modern 26B LLM onto decade-old Xeon CPU, and it fundamentally changed the economics of AI. The challenge was brutal, a modern transformer model demanding colossal throughput, running on hardware designed for enterprise virtualization from the early 2010s. Standard approaches fail. The memory bandwidth and computational units of a legacy Xeon simply cannot handle the sheer scale of 26 billion floating-point operations. So, we didn't try to speed up the CPU. We minimized the problem itself. Our focus shifted entirely to aggressive compression. The first hurdle was quantization. We moved far beyond typical 8-bit approaches, diving into custom mixed precision formats. By strategically applying adaptive low-bit quantization to the weights and activations, we achieved near acceptable fidelity while reducing memory footprint by over 75%. But compression alone wasn't enough. We needed to address the I/O bottleneck of the CPU cache hierarchy itself. This led us to custom memory mapping. We didn't treat the model as one contiguous block, we segmented it into cache-friendly chunks. We implemented a hybrid page-level swapping mechanism that predicted access patterns and prefetched the next necessary tensor block into the L3 cache before it was needed. This predictive loading masked the latency inherent in accessing slower main memory, a crucial trick for aging hardware. Now that the data is efficiently present, we tackle execution. Matrix multiplication on a CPU requires parallelization. We utilized the Xeon's multiple cores by mapping different linear layers to different physical threads, balancing load across all available execution units. The key was ensuring data dependencies were minimized between these parallel tasks. We restructured the inference graph to favor embarrassingly parallel computations. This transforms the execution from a strict serial bottleneck into a highly concurrent pipeline. Finally, the decoder. Even the final text generation needs to be efficient. We used optimized beam search implementations tailored for low-precision arithmetic. This combination of compression, predictive loading, and parallel execution is the blueprint for viability. The result? We moved the generation latency into an acceptable operational range for real-time, low-throughput edge applications. This achievement proves that high-performance AI doesn't always require the highest-cost hardware. It's about deep algorithmic thinking, making the hardware conform to the software, not vice versa. For fellow engineers facing deployment constraints, the lesson is clear: optimize your stack from the ground up. The barrier to entry for running powerful LLMs has shifted from hardware budget to software ingenuity. If you want to see the complete code base and benchmarks for this extreme optimization journey, check the description below.